Hello everyone, today we are going to talk about Fermat's little theorem. This theorem states that if P is a prime and A is an integer, then we have A to the P is congruent to A mod P. Also, if P does not divide A, then A to the P minus 1 is congruent to 1 mod P. If you are interested in proofs, you can search online or contact me through my email. I'm not gonna show that during videos. But this theorem is very helpful to deal with questions. And now let's see some questions related to Fermat's little theorem. The first one is to determine the remainder of 85 to the 61 plus 19 to the 86, all of them to the power of 2 by 13. So from Fermat's theorem, we know that 85 and 13 or 19 and 13 are relative prime, so we can use the theorem. So the theorem says that 85 to the 12 is congruent to 1 mod 13. Thus, 85 to the 12 to the 5 is congruent to 1 to the 5 mod 13, which is 85 to the 60 is congruent to 1 mod 13. Now for 85 to the 61, we just times 85 to the 61. We just times 85 on both sides. So 85 to the 61 is congruent to 85 mod 13. The same part is for 19 as well. So 19 to the 12 is congruent to 1 mod 13. 19 to the 12 to the 7 is congruent to 1 to the 7 mod 13. So 19 to the 84 is congruent to 1 mod 13. And we times 19 squared on both sides. We have 19 to the 86 is congruent to 361 mod 13. Therefore, 85 to the 61 plus 19 to the 86 is congruent to 85 plus 361, which equals to which is also congruent to 446 mod 13. For 446, which is divided by 13, we have 39, 56, 52. We have the remainder of 4. So 446 is congruent to 4 mod 13. And now we are finding the whole thing to the power of 2. So we have 4 squared is congruent to 3 mod 13. Thus, we find the remainder of this thing by 13 is 3. The next question is to find prime P such that P divides 11 to the power of P plus 19. So from Fermat's little theorem, you have 11 to the power of P is congruent to 11 mod P. Thus, we add 19 on both sides. We have 11 to the power of P plus 19 is congruent to 30 mod P. However, the question asks to find prime P such that P divides 11 to the power of P plus 19, then this means that 11 to the power of P plus 19 is congruent to 0 mod P. Now we have 30 is congruent to 0 mod p. Thus, the prime p can equals to 2 or 5 or 3. And now we solve the question. Now let's look at the next question. Prove that if p is congruent to 3 mod 4 and p divides x squared plus y squared, then p divides x and p divides y for x, y are integers and p equals to a prime. Notice that if p divides x, in this case, p must divide y. So let's suppose that p does not divide x or y. Then we have x squared. You can change this form to congruences, which is x squared is congruent to negative y squared mod p. For p is congruent to 3 mod 4, you can change this form into p equals to 4k plus 3, where k is an integer. So notice that p minus 1 equals to 4k plus 2, and p minus 1, which when p minus 1 divided by 2, you have 2k plus 1. And 2k plus 1 is an odd number, so we can have this power into x squared and negative y squared. So x squared to the power of p minus 1 over 2 is congruent to negative y squared to the power of p minus 1 over 2 mod p. And this equals to x to the power of p minus 1 is congruent to negative y to the power of p minus 1 mod p. However, from Fermat's little theorem, we have when x and p are relative prime, then x to the p minus 1 is congruent to 1 mod p, and negative y to the p minus 1 is congruent to negative 1 mod p. Thus, this has changed into 1 is congruent to negative 1 mod p, which means that p divides 2, and this cannot happen. So this is a contradiction. Thus, p must divide x or y. And an important thing in this question is that you can use this property for primes in the future. Like if p has the form of p is congruent to 3 mod 4, and p also has the form that divides x squared plus y squared, then we can use this conclusion from this question that p divides x and p divides y. Now let's look at the last question. Let n be a positive integer. Show that 2 to the 2 to the 800 n plus 3 plus 23 is a composite number. Let's make some number out of 23 and make a combination of this number, and to show that both number is a composite number. So first, let's take 2 out of 23. So 2 to the 2 to the 800 n plus 3 plus 2 plus 21. And 21 is divisible by 3 and 7. So let's try to show that this number is divisible by 3. Then it is a composite number. So you can simplify this as 2 times 2 to the 2 to the 800 n plus 3 minus 1, because we take one of the 2 out of the 2, plus 2, plus 1, I mean. For 3, we have 2 is congruent to negative 1 mod 3. And let's see this power, which is 2 to the 800 n plus 3 minus 1. This is definitely an even number because it is a power of 2. However, when I subtract 1 from the even number, this whole number becomes an odd number. So if I take the power of 2 to the 800n plus 3 minus 1, that's an odd number. Right side is still -1 because it is an odd number. Thus, 2 to the 2 to the 800n plus 3 minus 1 is congruent to -1 mod 3. And this is 2 to the 2 to the 800n plus 3 minus 1 plus 1, which is just this number. So we show that this number is divisible by 3, and 21 is divisible by 3. So this whole number is divisible by 3, and it is a composite number. So if you have questions, please contact my email, or if you need more questions, I can also provide to you. And this is a lecture for Fermat's little theorem. See you next time.